So far, we've been looking at problems where the pressure has remained constant, the temperature has remained constant, the volume has remained constant. Very common in problems that we want to change those conditions. So we're still going to start from the ideal gas law, PV equals nRT. The only variable in this equation that we cannot change is the gas constant R. So if I solve this equation for R, I'm going to bring the N and the T over to the left by dividing them. So if I start with a gas and I have the first pressure, the first volume, the first number of moles, and the first temperature, I can call those, instead of just P, I'm going to call it P1, and V1, N1, and T1. And by the ideal gas law, that equals R. Then, let's say I squeeze on the balloon. So I change the volume. When I squeeze the balloon, the pressure inside goes up, so the volume is changing, the pressure is changing. I can heat the balloon up and change the temperature, or I can put a little hole in the balloon and let some of the gas out, so the number of moles will change. So I will have a new pressure, a new volume, a new number of moles, and a new temperature. And according to the ideal gas law, that still equals R. Well, the blue equation equals R, the black equation equals R, so if they both equal the same thing, they both have to equal each other. So P1 V1 over N1 T1 equals P2 V2 over N2 T2. Notice all we did was start from PV equals nRT, the ideal gas law. And we can change 4 variables, pressure, volume, moles, and temperature, or we can just change some of those variables in a given problem. As an example, we start with 3 liters of a gas at this temperature and this pressure, and then we compress it, so we're changing the volume, and we want to know what's the final pressure. When you read a problem like this, if there is no description of the new temperature, then this temperature is assumed to be constant the way the question is worded. So we see 2 different volumes, 2 different pressures. So we're going to use P1 V1 over N1 T1 equals P2 V2 over N2 T2. If anything is the same for the first set to the second set of conditions, then we can cancel it out, such as this temperature. T1 is the same as T2, so we can cancel that out of the equation. Also, notice in reading the question, they don't say we put in extra gas or we popped a hole and let some of the gas out, so that means the number of moles is the same. So we've reduced our equation to just P1 V1 equals P2 V2. And we want to solve for the final pressure P2, so we can divide V2 over to the left. So my final pressure equals my first pressure, which was 2.5 atmospheres, times my first volume, which was 3 liters, and divide that by my final volume to 0.8 liters. I'm at constant temperature, so I know my T's are canceling out. I check my units, liter cancels liter, and I'm left with an answer of 9.4 atmospheres. For a problem like this one, you can think about the answer If you make the volume go down, this is like squeezing on a balloon. If you squeeze a balloon too much, it'll pop because the pressure goes up. When the volume of the balloon goes down, the pressure inside goes up. So a pressure of 9.4 makes sense compared to the first pressure of 2.5.